The butterfly effect, chaos theory, and the math of fate. If the universe follows rules, why does so much of life still feel impossible to predict? That question sits at the center of one of the most unsettling ideas in modern mathematics. The butterfly effect is often reduced to a slogan. A butterfly flaps its wings in one place, and a storm appears somewhere else. It sounds poetic, almost mystical, as if chaos theory were simply a fashionable way of saying that everything is connected. But the real idea is more precise, more dangerous, and far more interesting. The butterfly effect does not say that the world is ruled by magic. It says something harder to accept. A system can be completely deterministic, governed by fixed equations, and still become unpredictable because tiny differences in its starting point grow too fast to control. The rules stay the same. The future still follows from the present, and yet, after a certain point, prediction collapses anyway. That is the end. Chaos theory did not destroy that dream by proving the universe irrational. It challenged it by proving that exact knowledge has a cost. In many real systems, even a microscopic error in the present can explode into a macroscopic error later. The future is not hidden because the rules are absent. It is hidden because precision decays. The most famous doorway into that realization opened in weather science. In the early 1960s, meteorologist Edward Lorenz was working with a simplified atmospheric model. This was not a giant modern forecast engine. It was a stripped-down set of equations designed to capture convection, warm air rising, cool air sinking, order giving way to fluid instability. At one point, Lorenz reran part of a simulation using numbers printed from an earlier run. He expected the system to repeat the same pattern. Instead, it drifted away and produced a different future. The reason was almost absurdly small. The printed values had been rounded. Lorenz, 1963 paper, Deterministic Non-Periodic Flow, gave the world one of its first clean mathematical windows into chaos. Out of three coupled differential equations came behavior that was not random in the usual sense, but never settled into simple repetition either. When those trajectories were plotted in phase space, they traced the now famous butterfly-shaped attractor. Two wings, endless looping, structured instability. That image matters because it shows what chaos is not. Chaos is not a system with no shape. It is not formless disorder. Lorenz's attractor has geometry. The system is constrained. It lives inside a recognizable structure. But no trajectory lands twice in exactly the same place, and close starting points peel away from one another over time. This is why chaos feels like a war between law and surprise. Order exists, pattern exists, limits exist, yet long-range prediction does not survive. Lorenz later pushed this insight further in his work on predictable. That point is easy to misunderstand. The butterfly effect does not mean every tiny event matters equally forever. It means some systems have sensitive dependence on initial conditions. In those systems, uncertainty grows, not instantly and not without structure, but steadily enough that your forecast horizon shrinks. For a while, prediction works. Then it degrades, then it fails. That is a very different claim from superstition. It is also much more useful. To understand why, imagine two pendulums. A simple pendulum swings back and forth. If you know its length, its initial angle, and the local gravity, you can predict its motion quite well. A double pendulum is another creature entirely. Add a second arm hinged to the first, start it from two nearly identical positions, and the motions rapidly separate. The equations still determine everything, but the ability to track the future now depends on absurdly precise knowledge of the beginning. This is the first emotional shock of. One of the clearest examples came from a deceptively simple equation used in population modeling. If you take a population ratio from one generation and feed it into a nonlinear growth rule, something remarkable happens. At low parameter values, the population settles to a stable point. Increase the parameter, and the system begins to oscillate between two values. Increase it again, and the cycle doubles. 2 becomes 4, 4 becomes 8, 8 becomes 16. Then the pattern shatters into chaos. This was the lesson Robert May drove home in 1976. Simple mathematical models could create very complicated dynamics. You did not need enormous machinery to generate unpredictability. A tiny equation, repeated again and again, could cross from calm into turbulence. That discovery changed the tone of the field. Chaos was no longer a rare meteorological curiosity. It was a property that could emerge from simplicity itself. The logistic map became the perfect teaching machine for T. Visually, it looks like a tree losing its trunk and becoming a storm of possibility. Mathematically, it says something severe. Complexity does not always need complex causes. Sometimes complexity is what simple rules do when they are iterated in the wrong regime. The genius of the logistic map is that it strips away excuses. There is nowhere to hide inside that equation. No massive weather front, no millions of moving molecules, no gigantic machine with too many parts. Just one number fed back into itself, again and again. If chaos can appear there, then unpredictability is not merely a symptom of crowded reality, it can be born from the logic of recurrence itself. This also gives chaos theory one of its sharpest visual lessons. If you watch the map for a calm parameter value, the future narrows quickly toward a single destination. If you raise the parameter, the future begins to alternate between a few possibilities. Raise it more, and those possibilities multiply until predictee. Then came one of the deepest discoveries in the entire story. Mitchell Feigenbaum found that the route into chaos through period doubling was not arbitrary. The spacing between those bifurcations shrank at a universal rate. Different nonlinear systems, with very different physical interpretations, shared the same scaling behavior. That is a stunning fact. It means chaos is not just the breakdown of prediction. It has architecture. It repeats. It carries hidden numerical order inside apparent disorder. Feigenbaum's constants became a kind of fingerprint for systems on the edge of chaos, showing that wildly different equations could belong to the same family of behavior. This is one of the reasons mathematicians were so captivated by the field. Chaos was not merely a collection of weird examples, it was turning into a structured territory. The same geometric logic appeared in fluids, electronic oscillators, chemical reactions, and population maps. This is where the butterfly effect stops being a metaphor and becomes a worldview adjustment. Because once you accept that deterministic systems can be predictable only for a limited time, the old image of fate begins to split into two layers. At the first layer, the universe may still be lawful. Causes produce effects. Dynamics unfold according to structure. Nothing in chaos theory requires mystical intervention or cosmic whim. At the second layer, observers live inside those dynamics with limited precision. We measure imperfectly. We round. We sample. We neglect. We never know the true starting point in full. So even if the future is in principle fixed by the present, it may still be inaccessible in practice. That is why the phrase, the math of fate, is both tempting and dangerous. Tempting because chaos theory really does touch the philosophical nerve that fate stories have always targeted. It tells us that the smallest difference can alter a path. Dangerous because it is easy to overstate the claim. Chaos theory does not say that any trivial act will transform the world beyond recognition. It does not guarantee cinematic chain reactions. It does not prove that every life event was 1 second away from another universe. What it says is subtler. In certain nonlinear systems, there are regions where uncertainty amplifies so aggressively that the future becomes effectively unstable to measurement error. That distinction matters, especially when people try to import the butterfly effect into economics, politics, biology, or personal life. Financial markets, traffic systems, ecosystems, epidemic spread, and power grids can all exhibit nonlinear feedback. Some of them may show chaotic features under the right conditions. But the real world is noisier than a textbook map. It contains shocks, interventions, institutions, incentives, and incomplete data layered on top of the dynamics. So chaos theory is not a universal excuse for H. That warning can be constructive. If you know a system has a short predictability horizon, you stop wasting energy on impossible long-range precision and start investing in faster measurement, faster response, and better resilience. In meteorology, that means frequent observations, ensemble forecasting, and constantly updated models. In infrastructure, it can mean redundancy and early warning systems. In ecology or epidemiology, It means watching for regime shifts before they become obvious. The lesson of chaos is not surrender, it is respect. This is why scientists often prefer the language of scenarios to the language of prophecy. Once sensitive dependence enters the picture, a single forecast line can become misleading. Better to ask how a cloud of possible futures evolves. Better to understand what remains stable across many runs and what becomes fragile. Better to identify thresholds where a system changes character than to pretend the far future is a single clean path waiting. This is one of the most powerful ideas in science because it changes what competence looks like. If you cannot extend the horizon forever, you stop pretending that certainty is the goal. You ask instead how fast error grows, which variables matter most, and where intervention has leverage before divergence becomes uncontrollable. Modern science, finance, engineering, and policy all live inside that shift. We build ensembles instead of single prophetic trajectories. We estimate risk rather than worship exact forecasts. We monitor instability, not just averages. We treat early conditions with more respect because we know some systems repay neglect with explosive surprises later. That is a quiet revolution in how intelligence works. Before chaos theory, the fantasy of mastery was often framed as a fantasy of enough data. Gather more numbers, refine the machine, and uncertainty will retreat. Chaos theory answered with a harder truth. Sometimes better data helps enormously. There is a practical name for that limit in many fields: the growth rate of error. If uncertainty doubles slowly, prediction survives. If it grows explosively, prediction dies early. This is why chaos theory is inseparable from humility. The question is never just, do we have the equations? The harder question is, how long do the equations stay useful once the real world enters with imperfect measurements? That is the line between theoretical determinism and operational knowledge. Seen that way, the butterfly effect is really about information. How much detail about the present survives into the future? How much is erased by the dynamics? How quickly does a system turn ignorance into visible difference? A chaotic system is almost like a machine for magnifying forgotten details. It takes what the observer failed to know and writes it back into the later state. That idea can feel almost tragic, but it also has a strange beauty. Look again at the Lorenz attractor. Maybe that is why the butterfly image survived. Not because it is literally about insects causing storms, but because it captures the emotional experience of living in a world where small differences can matter without warning. The image turns a technical result into a human intuition. We all know what it feels like to stand in one moment and realize later that it was a hinge. But chaos theory asks us to go beyond that feeling. It asks us to become mathematically honest about what a hinge really is. A hinge is not any minor event we choose to romanticize after the fact. A hinge is a point inside a system where trajectories nearby can separate, where feedback amplifies difference, where prediction becomes expensive, fragile, and eventually impossible. The poetry comes later, the structure comes first, and that has consequences for how we think about fate itself. Classical fate is usually imagined as inevitability. Chaos modifies the picture. It suggests a world in which outcomes are not just certain or random, but deeply contingent on how small differences unfold. It means the future is not blank, and it is not fully legible either. It means control is local before it is global. It means tiny uncertainties are not always harmless. It means systems can look calm while storing the geometry of divergence underneath. And it means that intelligence, in the deepest sense, is not the conquest of uncertainty, but the study of where certainty ends. So the butterfly effect is not really about butterflies at all. It is about the price of precision. It is about why a lawful universe can still outrun the observer. It is about how simple equations can produce futures too intricate to compress into intuition. And it is about why the most unsettling thing in mathematics is not that the world lacks order, but that order itself can generate surprise. The real lesson of chaos theory is not that fate controls everything. It is that in some systems, fate and forecast are not the same thing. The laws may decide, but the decimals decide whether we can.